As you settle into the quiet of your night, it's hard to imagine the chaos unfolding in space. Right now, millions of rocks, traveling from other star systems, are silently drifting through space, right between us and the Sunday, and you didn't hear about this on the news. In fact, telescopes never found them. It was the nuclear launch warning satellites, monitoring for missiles, that first recorded these objects. These sensors, designed to detect the flash of missile launches and re-entering vehicles, have been tracking impacts for years, yet nobody paid attention. But these rocks, some of which hit us with the force of atomic bombs, have been a silent threat. The material of these rocks doesn't match anything else in our solar system. Harvard scientist Avi Loeb says it's time we figure out what these mysterious objects are before the next one arrives. Stay with me until the end, because the reason we missed a whole swarm of rocks from another star is even stranger than the swarm itself. Click subscribe and follow along, because this discovery is just the beginning. Meteors are still speeding through our atmosphere, and their origins remain uncertain. You'll want to be here when the next one hits. Let's dive into something unsettling. This isn't just about astronomers discovering a far-off visitor from another star system. It's about realizing that a swarm of rocks from between stars is already here, floating silently inside Earth's orbit right now. This revelation comes from Avi Loeb and his colleague Amir Siraj, who, along with data analyst Jason Chloe, published a study. They used data from the Center for Near-Earth Object Studies, CNEOS, Fireball catalog, and discovered something chilling. These aren't your typical meteors. According to their analysis, 2 rocks that hit Earth were moving so fast that their speeds exceeded what objects born in our solar system should be capable of. They were hyperbolic, which means they came from somewhere else entirely. This finding led Loeb's team to estimate that there could be tens of millions of similar meter-sized rocks from other stars floating within 1 astronomical unit, AU, from the Sun, 93 million miles, the distance between the Earth and the Sunday. Now, let's take a moment to appreciate just how mind-blowing this is. For centuries, we've assumed that the space between planets is relatively empty, mostly just sunlight and the occasional dust grain. But Loeb and his team suggest that this region might be teeming with rocks from other stars, and Earth keeps running into them. Here's the chain of logic they used, which frankly is as elegant as it is terrifying. You start with 2 meteor impacts. From these, you can calculate how often Earth's atmosphere is struck by rocks of this kind. Then you can estimate the density of these rocks in space, how many of them must be floating around for us to encounter them at the rate we do. When you multiply that density by the volume of space inside 1 AU, about 93 million miles across, it leads to a staggering number, tens of millions. Imagine this. Earth is like a car driving down a highway at 67,000 miles per hour, surrounded by invisible hailstones. You might only notice them when they smash into your windshield, or in our case, our atmosphere. Most of the time, these rocks burn up harmlessly, but once in a while, one hits with the force of a bomb. But why is this information coming to light now, in 2025? It's not because telescopes got better. The story starts with a shift in error models and someone finally looking at old data in a new way. For years, the CNEOS catalog, a public collection of fireball detections from government sensors, sat there with uncertainty estimates attached to each event. No one thought to reanalyze it in depth, until in 2025, a study led by Pina Asensio fixed the data, comparing it with ground-based meteor networks. These networks are transparent, scientifically checked, and provide a more reliable standard. The result? A more accurate dataset post, 2018, one that Loeb's team could trust. And within this newly corrected data, they found the 2 rocks that were moving in ways that suggested they came from other stars. This isn't just an academic curiosity. It opens a new chapter in understanding our cosmic neighborhood. While in 2024, astronomers tracked a comet named 3 Atlas from another star system, the rocks Loeb talks about are different. They are too small to see until they hit us. We can't track them in advance. They only show up when they've already entered Earth's atmosphere and burned up at high altitudes. These objects behave in ways that are difficult to predict and track, and the implications are enormous. For years, scientists believed rocks from other stars were rare and unusual, but what if we've been looking at the wrong thing in the wrong way? Perhaps the swarm of meter-sized rocks is more common than we realized, and our current tools are only catching the largest objects. If this swarm is real, it would mean that the inner solar system, once thought of as a clean zone, is actually much messier than we've ever imagined. The material from other stars wouldn't just be a rare oddity, it would be a constant, invisible presence. And we'd only notice it in rare, impactful events. The data is still early, but the idea that millions of these rocks are floating through our solar system right now challenges everything we thought we knew about space. But remember, the core of this claim is based on just 2 events. This is both thrilling and terrifying. A conclusion built on such a small sample is risky. That's why Loeb's team takes the findings seriously, but acknowledges the limitations. What makes this story even stranger is the source of the data. This discovery wasn't made by astronomers using high-powered telescopes. It came from a set of sensors that were originally designed for nuclear launch detection. These sensors, part of the U.S. military's missile warning network, were watching for missile plumes and re-entering rockets. It's a completely different application from what astronomers use, but those sensors picked up these rocks and recorded their impacts. What's even more intriguing is that the catalog of data they compiled, the CNEOS Fireball catalog, doesn't include the full technical breakdown of each detection. The raw sensor data is classified, and so scientists are forced to rely on indirect methods, like cross-checking the data with more transparent sources. That's where the work by Asensio and others becomes essential. It gives credibility to Loeb's findings, even though the full details remain elusive. Now, let's pause for a moment and consider how we missed an entire swarm of rocks from another star. It might sound strange, but it's true. Astronomers have been missing something that's been right in front of our eyes. The catalog that holds this data, known as CNEOS, has been public for years. But despite its significance, it wasn't until 2025 that anyone really began to understand its implications. For years, these records sat there, untouched, like an old phone book full of fireball detections. However, the uncertainty estimates that came with those detections weren't very clear, and that made it harder to trust the data. But something changed in 2025. A study by Pina Asensio changed everything. Asensio and her team compared the data from CNEOS against the data from ground-based meteor networks. These networks use instruments that are completely open and scientifically verified, offering a more transparent way to measure meteor activity. The result was significant. After 2018, the CNEOS data became far more reliable. With this new insight, Avi Loeb and his colleagues were able to uncover 2 meteor impacts that had never been fully appreciated before. The implications of these findings, well, they're nothing short of game-changing. Let's take a closer look at the math behind Loeb's conclusions. From those 2 detections, his team was able to estimate how frequently Earth's atmosphere encounters these hyperbolic meteors. With this data, they deduced the density of these rocks in space. And when you multiply that density by the massive volume of space inside 1 AU stretching from the Sun to Earth, about 93 million miles, you get a mind-boggling number. Tens of millions of these rocks are likely out there right now. Imagine that. Millions of rocks from other star systems, silently drifting through our solar system, and we never noticed them until now. They're small enough that we can't see them coming, but large enough to cause significant damage when they hit. Most of the time, these rocks burn up harmlessly in the atmosphere, but every so often, one hits with devastating force. And when it does, the aftermath is something we can measure, something we can track and analyze. But the key is that we've been completely missing these smaller rocks. We've been looking for large objects like comets or asteroids that are easier to detect, and we've overlooked the ones that really matter. This opens up a new understanding of what's going on in the inner solar system. The space between planets isn't just a clean void. It's a bustling highway of debris from other star systems, constantly flowing into our own. In fact, if Loeb's estimates are correct, the amount of this debris could be staggering. The solar system is far messier than we thought, and these invisible rocks are part of a background hum, a constant stream of material from stars that existed long before our sun was even born. And it's always been here, just under our noses, unnoticed. But let's be clear, Loeb and his team aren't claiming this as absolute proof just yet. This is still early analysis based on only 2 data points. From a statistical perspective, that's a dangerous place to build conclusions. The data, though interesting, is still limited. The sheer scale of the claim, the idea that tens of millions of rocks from other stars could be silently drifting through the inner solar system, is enormous. And as thrilling as it is, it's also deeply unsettling. If this hypothesis holds true, it could completely alter our understanding of space and the environment we're living in. But for now, it's just a hypothesis. And that's the tricky part. We're not dealing with clear-cut evidence yet. What we have are estimates, models, and a significant amount of speculation. Still, those estimates are based on real data that's only now becoming reliable thanks to the work of teams like Asensio's. So, what would it mean for us if the claim is true? It would mean that our understanding of space is fundamentally flawed. It would mean that these objects from other stars are not rare novelties, but part of a much bigger picture, a constant flow of material coming from the broader universe. This leads us to the next question. What are these objects made of? And why, in some cases, do they seem to be tougher than anything we've ever encountered in our solar system? Some of these rocks appear to have an unusual strength, stronger than any meteorite we've ever seen. Typically, when meteorites hit Earth, they burn up at high altitudes, breaking apart before they reach the ground. But these rocks seem to survive longer and penetrate deeper into the atmosphere. Why? What are they made of? Let's take a moment to dive into this. When a meteor enters Earth's atmosphere, it faces extreme friction. The heat generated by this friction causes the rock to fragment and vaporize, turning into a streak of light. Meteorites made of common stony materials typically break apart relatively high in the atmosphere because they aren't strong enough to withstand the intense pressure. But the rocks that Loeb and his team are tracking seem to have unusual resilience. They fragment much deeper in the atmosphere than ordinary meteorites, suggesting they might be made of something much tougher. This is an important observation, and it adds another layer of mystery to the story. Could this simply be a matter of measurement error? Perhaps. It's possible that the strength estimates for these rocks are inaccurate. But there's another possibility. Maybe these rocks are made of a material we've never encountered before, something far stronger than any meteorite in our solar system. Or here's where things get really interesting. What if these rocks aren't even natural at all? Now, let's dig into what makes these rocks even more mysterious. The strength of some of these objects is unusual, so much so that it's raising some uncomfortable questions. When a meteor enters Earth's atmosphere, the extreme forces it faces cause it to break apart. The less resilient the rock, the sooner it will fragment, usually higher up in the atmosphere. Most meteorites we encounter are stony, and their material isn't very tough. As a result, they tend to break up at around 50 kilometers above Earth's surface, but the rocks Avi Loeb's team is investigating seem to have an unusual durability. They break apart deeper in the atmosphere at altitudes of 30 kilometers or lower, and this suggests something about their composition. These rocks appear to be much tougher than any meteorite we've ever encountered in our solar system. At first, this might seem like a small detail, but it isn't. The material strength of a rock, the amount of stress it can endure before breaking apart, gives us key clues about its origin. If a meteorite behaves like it's made of something tougher than anything we've seen before, we have three possible explanations. 1. The measurement could be wrong. 2. The rock could be a natural material we've never encountered, perhaps formed under conditions that don't exist in our solar system. Or 3. It might not be natural at all. Let's start with the natural explanations first. It's possible that these rocks are made of metal-rich materials, forged under extreme conditions in another star system. Perhaps they were formed in the core of a planet that was destroyed in a supernova or a planetary collision, compressed and heated in ways we don't fully understand. Maybe they were created in environments with extreme pressure places we don't see in our solar system. Another possibility is that they've been exposed to cosmic rays or other forms of radiation during their long journey through interstellar space, altering their structure and making them stronger than normal meteorites. All of this is speculative, but it's plausible. These rocks could have been subjected to forces that we simply don't encounter in our solar system. However, there's another possibility that's even more unsettling. Could these rocks be artificial? Could they be something made, not by nature, but by an advanced civilization? This might sound like science fiction, but let's explore the idea. The hypothesis of artificial origins is often dismissed in scientific circles, but the fact is that we can't rule it out completely. If these rocks are unlike anything we've ever seen, and if they behave in strange ways, surviving atmospheric entry longer than expected, it raises the possibility that they're engineered materials designed to withstand harsh conditions. One theory involves the creation of self-replicating machines, which are a concept introduced by mathematician John von Neumann. These machines, often called von Neumann probes, would be sent out by an advanced civilization to explore other star systems. They could gather resources, replicate themselves, and send their copies to new systems. Over millions of years, such probes could fill an entire galaxy. If we apply this idea to the objects Loeb is studying, what if some of these interstellar rocks are not natural at all? What if a tiny fraction of them were once part of a failed mission or an ancient probe? Imagine a probe that malfunctioned, or even a fragment from an alien civilization that left it behind. Of course, this is pure speculation, but it's grounded in real scientific principles. And when you consider the numbers, it becomes even more intriguing. Remember, Loeb's team estimates that tens of millions of meter-sized rocks from other stars could be floating within 1 astronomical unit. If only a tiny fraction of these rocks were artificial, let's say just 0.01%, that still leaves us with thousands of objects. Thousands of potential artifacts drifting through our solar system, unnoticed and undetected. It's a startling thought. What would such objects look like if they were artificial? They wouldn't be flying saucers or alien ships. They would likely look like ordinary meteorites, strange, tough, and inexplicable, but without the obvious markers of technology. They could be lumps of metal or composite materials built to survive the harsh conditions of space travel, and they might pass by unnoticed because we're not looking for them. This is where the story starts to blur the lines between science and science fiction. While the natural explanations for these objects are still plausible, we can't entirely rule out the idea that some of them might be technological debris. Maybe the universe isn't as empty as we think. maybe the sky isn't as quiet as we've always assumed. Perhaps these rocks are the remnants of ancient alien civilizations, or even the unintended consequences of failed extraterrestrial missions. But let's take a step back and remember that this is still a hypothesis. The idea of artificial rocks is still speculative. And even if these objects are made of material we don't recognize, that doesn't necessarily mean they're from a different civilization. It's just as likely that we simply don't understand their true nature yet. Science is full of anomalies that turned out to have mundane explanations once we understood the context better. However, there is one part of this story that's undeniable. The mystery surrounding these interstellar visitors is growing. The fact that we're only now starting to notice these objects, despite the fact that they've likely been drifting through our solar system for millions of years, means we're still on the cusp of understanding. If we are indeed looking at something truly extraordinary, it will require a lot more than just theoretical work to solve. We'll need evidence. We'll need material samples that we can study directly, rocks we can hold in our hands, analyze in laboratories, and explore in ways we've never done before. Let's dig even deeper into this possibility. If these interstellar rocks are not just strange natural objects, but could potentially be artifacts, how would we go about proving that? Well, one crucial piece of evidence is something tangible, something we can hold in our hands and study under controlled conditions. So far, we're still missing that key piece, the material itself. The analysis of the rocks from other stars relies heavily on the data from their atmospheric entries, but without physical samples, the case remains theoretical. Scientists are working under the assumption that the material we need is somewhere out there, but as of now, we don't have it in hand. To understand the magnitude of this, imagine a forensic investigation without the actual crime scene. In this case, the crime scene is the impact event that creates the fireball, and the missing evidence is the rock itself. We can look at the trajectories, the velocities, and the impact data, but we can't conduct the necessary lab tests to confirm what these objects are made of unless we recover the material. Without it, we're left to speculate based on indirect observations, and even the most interesting hypotheses remain just that, hypotheses. So what would it take to actually recover these objects? Well, scientists have already proposed one way to gather more concrete evidence: an ocean expedition. Avi Loeb's team, for example, launched an ocean mission to retrieve spherules, tiny molten droplets from the seafloor near the impact site of one of the alleged interstellar objects. They hoped that these spherules would give them some insight into the composition of the original rock. However, this is where things get tricky. Critics have raised concerns about contamination. The ocean is full of industrial pollution, volcanic activity, and even shipwrecks, all of which could introduce foreign particles. Proving that a specific spherule came from a specific meteor is incredibly difficult. The chain of custody is vital here. Without it, we can't say for sure that the spherule is connected to the impact site. It's a thorny issue, and the skepticism surrounding these attempts to gather evidence is understandable. If you're going to argue that an object has an origin in another star system, you need undeniable proof. Unfortunately, we don't yet have that. We can't say for certain whether the spherules are genuinely from an interstellar rock or simply from another source entirely. As much as the ocean expedition and other recovery missions might help, they're not the final word. That's where the concept of material strength becomes essential. If we were to recover a sample of one of these rocks and study it, we could analyze its structure and determine whether its material strength really does exceed what we know about typical meteorites. This could help us understand whether these objects are simply unusual natural rocks or something else entirely. But until we have a sample, the question remains open. Here's where it gets even more speculative. If we accept that there might be artificial objects mixed in with these interstellar rocks, fragments from ancient probes, or even alien artifacts, then what does that mean for us? It raises the possibility that the objects we're encountering might not be from just any star system. They could come from advanced civilizations that existed long before our sun even formed. Or perhaps these objects could be the leftovers of alien missions that were sent out to explore the galaxy millions of years ago. It sounds like science fiction, but the numbers are compelling. Tens of millions of rocks could be floating silently through our solar system right now, and even a tiny fraction of those could be artificial. Let's consider this idea. If only 0.01% of these objects were artificial, that's just 1 out of every 10,000 rocks. That still leaves us with thousands of potential artifacts scattered throughout the inner solar system. Even if the majority of these objects are natural, the very notion that we could be dealing with thousands of extraterrestrial artifacts is enough to make us rethink everything we know about space exploration and extraterrestrial intelligence. Now, let's be clear, this is all speculation. We don't have any solid evidence of artificial rocks yet. But the idea is fascinating and should at least prompt us to ask, what if we're overlooking something massive? What if we're missing an entire category of objects, tiny, difficult to detect, but potentially incredibly significant? One of the key questions in all of this is how these objects behave when they enter Earth's atmosphere. Meteors from our solar system usually break up at high altitudes, but the objects Loeb's team is studying seem to survive longer, burning up deeper in the atmosphere. If they're indeed tougher than ordinary meteorites, it might point to a different kind of material, something that's either manufactured or created under extraordinary conditions. Even if these rocks are natural, their unusual behavior is enough to make us reconsider how we classify meteors and asteroids. The scientific community is still divided on the interpretation of these findings. Some argue that the evidence is too thin to make any bold claims, while others, like Loeb, are pressing forward with the idea that we've been overlooking a huge chunk of the cosmic puzzle. The key to unlocking this mystery is more data and, hopefully, a physical sample. But even with that, the question remains, if these objects are not from our solar system, what are they, and where do they really come from? As we continue down this path of investigation, things only get more intriguing. The idea that we could be surrounded by interstellar objects, some of which might not even be natural, challenges everything we've ever assumed about space. And here's the kicker. We're not just dealing with 1 or 2 strange occurrences, but potentially a whole class of objects we've failed to recognize: smaller rocks, seemingly inconspicuous, but with qualities that defy our understanding of what's possible in the cosmos. So, what happens if this claim is true? If tens of millions of rocks from other stars are indeed drifting through the inner solar system, silently orbiting the sun, along with everything else, it would radically change our perception of the space around us. Our solar system wouldn't be the pristine, orderly region we once thought it was. Instead, it would be a crossroads, a chaotic space where material from other star systems is constantly entering, interacting, and influencing the dynamics of our own environment. These interstellar objects could be a part of the solar system's constant refreshment, constantly introducing new material from the wider universe.